We're more or less covering Chapter 5. Chapter 5 is pretty big and it has lots of details in it, and I strongly urge you to read it. If you didn't have a college level course in probability and statistical inference, you absolutely have to read it. If you did have one, you still should read it, because it will be a refresher, and also it will put it in the context of what we do in machine learning. The kind of questions we would like to be able to answer after today, there are 3 such questions. One we've already dealt with, and that is, given a hypothesis and some kind of distribution of inputs, curly D, what is the true error of this hypothesis? We dealt with it quite a bit, especially in Chapter 7, but it has a different flavor to it now, but let me write it anyway. I'll just write it off to the side. We will not need to look at it much, but I want to give you the whole context. Can you see this? Okay. So the first question is, given H and curly D, what is, maybe also given some set D. So this is a given hypothesis, this is the distribution curly D, and this is some finite set of data that was sampled from curly D. It could be the training set, a test set, you can also call it S for some test set. What is the error of the hypothesis H under the distribution curly D? This is what we call true error. And we talked about the difference between true error and the error under any finite sample. Let's say the training set error or some test set error. We talked mostly about the difference between the training set error and the true error. This is number 1. I'm just going to give you a quick preview. I apologize to those of you here, but you don't really need to see that much. Question number 2 is given 2 hypotheses, H1 and H2, and D and S, the curly D, the underlying distribution of the data, and some sample. Is H1 better than H2? Namely, is the error, the true error of H1 less than the true error of H2? True error is written as error with the subscript of curly D of H1 less than the true error of H2. Okay, so the first question is, given one hypothesis, what is its true error? The second question is, given 2 hypotheses, is one of them better than the other in terms of error? And the third question we're going to ask is, given 2 learning algorithms, LA and LB, and of course there's a curly D in the background, and maybe some set, or more than one set, is LA better than LB? Now we'll have to define what we mean by better. Anybody wants to suggest what we mean by better? Please.
Well, it gets on S, it gets that smaller error than LB.
Okay, it gets a smaller error on S. So you apply it to S. You use S what, as training or as test? As training. So you use S as a training set. You train algorithm A and algorithm B. They give you hypothesis, let's say HA and HB, and then you check, and then you somehow try to figure out which one has.
Partition S.
Maybe you partition S into training and test. You take the training part, you train both LA and ALB on it, you get 2 hypotheses, HA and HB. Then you take the test data and you measure the error of HA and HB on the test data, and if HA gives you a lower error?
That it's better than HB.
Okay.
If you were able to answer 2, then we can actually do this for the true error, but I don't know if it's possible.
Yeah, if you could answer 2, if you could figure out the true error of some given set of hypotheses, then you could also plug it into here. So you can see this being a component of this, and this being a component of this. Right? Do you see any other problems or anything you would want to change or improve on in Dan's definition of what it means for L1 to be LA being better than LB?
Sample complexity?
I'm sorry?
Sample complexity.
Sample complexity. Okay, so there are other dimensions of being better. One algorithm could require less data to achieve a certain goal, or can take less time. Very true. Let's just evaluate them on error rate. Just to summarize what Dan was saying, if you want to know which one results in lower error rate, you take your data, you split into training and testing, you train them both on the training part, you take the hypothesis came out, test them both on the test set. How much do you trust your answer? Is it possible that somebody else would take the same 2 learning algorithms and end up with different answer?
If they partition as in different ways.
If they partition data in different ways. Okay. True. Why?
Because you are using part of it as in training and part of it in testing.
Mm-hmm.
So it depends whether, it depends how you partition the data into 2 parts. That will be different.
Right. So the important thing here is that a learning algorithm is not the same as the hypothesis that came out of the learning algorithm, because a learning algorithm can have some properties in general, but it may one day hit upon a bad, quote-unquote, bad training set. So you really, if you evaluate a learning algorithm, you want to evaluate how it behaves on the whole distribution of training sets, how it behaves on average on training sets. Right? So you could be in a situation where one training set will produce a better HA than HB, and a different training set will produce a better HB than HA. So when you move from a learning algorithm to a hypothesis, you're implicitly choosing some finite sample to work with, and sometimes the choice will be better than others. The same thing is true for evaluating the error of 2 hypotheses on some finite set. On one set, HA would have a lower error rate, on another set, HB would have a lower error rate, right? So what I'm trying to get you to recognize here is that there's inherent variability in going from algorithm to hypothesis and going from hypothesis to error rate. 2 different sources of variability. And what we mean by is LA better than LB is algorithm A on average produces hypotheses that on average get lower error rate. Does LA produce H's that on average are better? I have to apologize to you guys there. Than LB's. So learning algorithm A will produce many hypotheses depending on what kind of training data you give it. Learning algorithm B will produce many hypotheses. We will say that LA is better than LB if on average the hypotheses that it produces are better than those that B produces. What does it mean for them to be better? It means, going back to this question, question number 2, for H1 to be better, for HA to be better than HB, it means that on average it has a lower error rate on some test set. Here we wrote it differently. We said that the true error is lower. But another way to write it is to say, if you draw test samples from curly D, on average H1s will be lower error rate than H2. So there's an N on average here too. 2 different on average. But the averages are over two different, slightly different things. What is the averaging here over? Louder, please. Sorry? Different test sets. All possible test sets. What's the averaging here over? All possible training sets. Now this on average may sound like sloppy language, but actually we mean something very concrete. We mean expectation. Expectation with regard to the curly D distribution. Okay, so this is our big plan. Now when we say we want to draw inferences to answer these questions, what's the true error rate? Is HA better than HB? Is LA better than LB? We're not going to be able to answer them deterministically. None of these three we can answer deterministically. Namely, we will not be in a situation typically where we can say, yes, this one is definitely better, 100%, no possibility of error. We're going to answer them probabilistically, using confidence intervals. So to do that, I want to give you a little refresher, either refresher or introductory course, depending if you've seen it before, on what statistical inference is all about. So what we're going to have here is the relationship between probability, I should put it in the middle, relationship between probability theory and statistical inference. And the relationship is reciprocal. One goes one way, one goes the other way. So on one side, we have a probability distribution with parameters. For example, it could be a binomial distribution with the parameter P of success and maybe N tosses of a coin. We're all familiar with the binomial distribution. It could be a normal distribution with a mean, mu, and standard deviation sigma. Or it could be any other distribution. Suppose we knew what the true distribution is from which our data comes. Then we could calculate, if we sample a certain number of times from it, we can calculate the probability of each possible sample. Example, suppose we knew that our distribution is of coin flips, and it's a binomial distribution with probability of head 0.6. And we sampled 10 times from it. How many possible outcomes are there if we sample 10 times? 11. There could be 0 heads, 1 head. I mean, I didn't define for you what an outcome is, but if I was interested in how many heads there are, there could be 11 possible heads from 0 to 10. Somebody else might be interested in the actual sequence. In that case, there are 2 to the 10. But if my variable of interest, if my statistic of interest is a number of heads, there could be anywhere from 0 to 10. I could calculate exactly the probability of getting exactly 5 heads, exactly 7 heads, exactly 9 heads, right? You're all familiar with the binomial expression, right? I'll write it on the board in a minute. But in principle, if you know the distribution, you can calculate the probability of any possible outcome. Sometimes it'll be mathematically difficult, most of the time it'll be straightforward. So this will be an arrow in this direction. This is probability theory. And here you have data outcomes. For example, 7 heads. Or in the case of normal distribution, some set of real values, x1, x2 through xn. Or in the case of some other distribution, it will be something else. There will be some particular data set that came out of sampling from this distribution. Okay? This is called probability theory, and it's basically math. You take the formula, you take the particular data set that you are interested in, or maybe the one that you observed, and you calculate what was the probability that this distribution function generated this data. Now you can also do the opposite. Suppose you don't know the distribution. You might know it's a binomial, but you don't know what the parameter is, the probability of head. Or you might know it's a normal, but you don't know what the mean and the standard deviation are. In general, you may know the general form of the solution, but you don't know the exact parameters. And now you have a data set that was generated from that distribution, and you're trying to go back and estimate or guess what the true value of the parameters was. So this goes from here to here, and this is called statistical estimation. Or statistical estimation theory. And this is the relationship between probability and statistics. One goes from distribution to possible data, the other one goes from an actual data set to possible values of the parameters. Now, it should be pretty clear to you that if you were told that there were 7 heads out of 10, you can't know for sure what the true probability of head was, right? If I take a coin and I flip it 10 times and I get 7 heads, somebody might say the probability is 0.7, but I think you're sophisticated enough to know that we really don't know that it's 0.7. It could be pretty much anything. It couldn't be 0, but it could be any other value. Now some values are more likely than others, but it could be any value, right? So we cannot come up with deterministic, foolproof answers, but we can come up with some qualified answers. If you got 7 out of 10 heads, what would you give as an answer? What kind of answers might you give? What is the true probability of head? Please?
7 times bounded by some margin of error. Times error.
Okay, so one answer would be, it will be 0.7 plus minus some margin around it. So you're giving me an interval. Okay. Alright. Now I may insist that you give me a single number. In which case, what number will you give me? .7. I mean, it's better than, it looks like it's better than any other number. And you could argue that that's true. You could also argue other things. Like if you know something about coins, and you know they tend to be balanced, you might actually say, I think it's 0.5. For one thing, the data, 7 out of 10, is not inconsistent with 0.5. I mean, it can certainly imagine a fair coin being tossed 10 times and getting 7 out of 10. So you can't think of 7 out of 10 as contradicting the 0.5 hypothesis, right? And you could argue that you know from your experience that coins tend to be balanced, unless you're in a magic show, okay? So you're bringing in your prior expectations, and that's okay too. So one way of producing estimates is by blending in prior expectations and the data you observed. That's called the Bayesian way of doing things. Did we talk about Bayesian estimation here? No? Okay. We're going to either this time or next time. But the big idea is that you're trying to combine together your prior expectation about what the value of the parameters might be, drawn from your knowledge about the world. For example, your knowledge that coins tend to be balanced. And your observation. Suppose you didn't observe 7 out of 10, but you observed 700 out of 1,000 tosses ended in the head. I suspect you will not say that 0.5 now. Right? I hope. It seems unlikely that a fair coin would produce, in 1,000 tosses, will produce 700 heads. It'll start making you very suspicious that maybe something's not okay there. If you don't agree with me with 700,000, you'll certainly agree with 700,000 out of 1,000,000. Anyway, one way of doing it is Bayesian. Bayesian means you bring in your prior expectation about the values of the parameters and you somehow combine it with the data that you saw. Another way of doing it is if you don't have any prior expectation, or you don't want to acknowledge that you have prior expectations, or you don't know how to capture your prior expectations, you can try to come up with methods for estimation that don't depend on the prior. This school of doing things is called frequentist. frequentist way of estimating parameters. Sorry. I just wrote the word frequentist here. Bayesian frequentist. I will talk to you a lot more about the philosophical differences between frequentist and Bayesian way of looking at things. But I should just point out this time that Bayesian thinking is, well, it's very prevalent at CMU. The CMU Statistics Department, for example, is one of the main, most prominent Bayesian schools of thought in the country, if not in the world. Although it's not strictly Bayesian, it's almost a religion at times. There's this dichotomy, doing things this way or that way. CMU is thankfully not dogmatic about it. I mean, people are comfortable with and appreciate the benefits of both sides, but you will see debate in the literature between the Bayesian and non-Bayesian way of doing things. You should know that even though Bayesian theory is very well developed for lots of practical things like drug approval, Bayesian theory is not accepted. And the reason is exactly this reliance on prior. It makes it subjective. You know, you cannot draw any conclusions in Bayesian framework without bringing in some prior. And if you bring in a prior, how do you know that your prior is good? Or is right, is correct? We'll talk a lot more about it. The frequentist way of doing things is agnostic of a prior. It says, just based on the data, I'm going to give you a confidence interval that if you use my method, 95% of the time your confidence interval will include the correct value. Okay, we'll talk about it again, but it does not say anything about a prior about the parameter values. It's rather than assuming that there's a distribution over the parameters, you assume that the parameters are not known, and you're just hunting for them. And you're going to put a confidence interval in some area, and you're going to argue that 95% of the times you do that, or 99% of the time you do it, depending on your choice of confidence, you will catch the beast. You will catch the right parameter value. If this seems a little nebulous to you, hopefully it will become clearer later. Okay, so this is how we're going to answer these three questions. We're going to answer it by doing this thing. Starting from data and deriving a method for bounding the true parameters in a confidence interval, as was suggested here. So, for example, the first question there, the true error question, we're going to treat the true error as a parameter. We're going to look at a set of data and go back and derive a confidence interval for the value of that parameter. If you think about the parameter of true error, it's very much like the probability of head, because true error over curly D is the same as sampling from curly D and saying what is the probability that something that was sampled from curly D will turn out to be classified erroneously by our hypothesis. So it's very much like flipping a coin that has a probability true error, curly D, of being head. Okay, a little refresher on how this thing is done. So to build the formula for finding confidence intervals, we actually start from this direction. So you start from the general form of the probability distribution, and you write down the expression for the probability of each possible outcome. And then you use that expression to go back and derive a confidence interval formula. So let's do it for the case of binomial distribution, probability of head, because this is the case we're going to be using for the true error. You have some variable that's distributed binomially with probability of head or of success P and n tosses of the coin. And you ask yourself, what is the, let's say X is defined as number of heads. In n tosses. So P is probability of head, and n is the number of tosses. And you can think to yourself that x could be measured as number of correctly classified instances, or incorrectly classified ones, depending on how you want to define it. And then you ask yourself, what is the probability that x will attain the value k? Namely, that a coin that was flipped n times comes out head k times, or a sample of n inputs, k of them are classified as correct or incorrect. And the answer to this is the standard binomial expression, n choose k, p to the k, 1 minus p to the n minus k. Hopefully you're very familiar with that. And we also know mathematically that the sum of p of x equals k, when k goes from 0 to n, all possible values must be 1. So if you take this expression and you sum it, k going from 0 to n, you'll get 1. Better be, because it sums over all possible outcomes. So you start by writing this equation, and typically when you write it, the way you think about it is that you know p sub h, and you don't know what k is. But you can now invert it in your mind and say, suppose I know what k is, what could p sub h be? And the logic is that if k, for example, is very close to n, then it's highly unlikely that p sub h is very small. If you got 9 out of 10 heads, it's very unlikely the probability of head is small, and vice versa. And this can then be used to invert the relationship, and I'm not going to go through the process with you, I'll just give you the form of the confidence interval formula. But what I want you to know is that it's derived from this. You start by writing down this direction, and then you use it to derive the formula for going back. Okay, let me first quickly run this by you. Okay, so this is the same binomial distribution that I wrote on the board before. What they call R here is what I call the K, and this expression n factorial divided by R factorial n minus R factorial is the same as n choose K. Right? I hope you're all familiar with it. What I wanted you to see here is what the expectation is of this value. The expected value of x, of the random variable x, namely the expected number of heads, is defined as the sum over all possible values of number of heads multiplied by the probability of getting that number, and this happens to come to n times p. Namely, if you toss the coin 100 times and it has probability of 37.37, then the expected value of number of heads you see is 37. And the variance, if you remember how variance is defined, is the expected value of the square deviation between the actual value and the expected value. So here's the actual value, here's the expected value, here's the square of the difference. The expected value of that is n times p times 1 minus p. Which means the variance grows linearly with the size of the sample, and it's greatest when p is close to half, and it's smallest when p is very large or very small. And then the standard deviation is defined as the square root of the variance, which means standard deviation grows as the square root of the sample size. So very intuitively, if you want to have a better estimate, of course you need a larger sample, but as your sample grows larger and larger, your accuracy gets better and better, but at a slower rate, at a rate that is the of your sample size. Okay, so this is all going in one direction. Now if I can only find my slides. Okay, here's just the result of going backwards, stated without the derivation. And it's stated now in a language of true error rather than probability of head, but it should be completely interchangeable for you. If your sample size has n examples, where n is at least 30, that were drawn independently of the hypothesis, we'll talk about why that's important. And you are curious what the true error is, namely what the probability of head is, then you take the error on the training set, what we called 0.7 before, and you bound it with plus minus a certain range. And the range is related to this expression, which should look to you familiar to you from the expression for standard error. If you remember, the standard error or the variance had p times 1 minus p. This is where this comes from. The square root comes from that as well. So the formula for bounding, for putting a confidence interval around the value that you observed in the training data, comes from the standard error of the distribution. Now conceptually there are slightly different things. The standard error that I showed you before, you start from knowing the value of the parameter, and you had a standard error for the outcome, for the value of the data, what k is, how many errors you observed. Here it's the opposite. You know how many errors you observed, and you're putting the standard error out to capture, hopefully, in your interval, the true value of the parameter. Okay, conceptually they're different. Mathematically they look very similar here. You don't need to copy this over, it's all in your slides, of course, in the book as well. Now, where did this number come from? This number is related to how confident you want to be that you are going to capture the true value of the parameter, namely the true error, in your confidence interval. It came from our choice of 95%. Typically in confidence intervals people use things like 95%, 99%, 99.9%, sometimes 90%, depends on your application, depends on how much you're willing to tolerate failure. So in that regard it's similar to computational learning theory. It's up to you to decide how much error you're willing to tolerate, or how much probability of failure you're willing to tolerate. Here is a more general form. So exactly the same conditions. We have that n greater than 30 condition there. And now the general formula is that if you want an n% probability of capturing the true error in the interval that you're setting, you should use this side interval where the n found its way to this n here. So z sub n. And z sub n, as you see, grows as your desired probability of success grows. If you want to be 99% assured, if you want 99% of the time that you use this procedure for it to succeed, to get the right value in the interval, you need to use 2.58 times this number. So intuitively, the more you want to succeed, of course, the bigger your interval should be. At some point, your interval might be so big that it will go outside the 0 to 1 range, which becomes meaningless, because you know that the true value is between 0 and 1. Right, so at that point, it won't be very useful to you. one way to combat it is to have a larger n, larger sample. But you can see again the dependence on the n. It's dependence via square root. Okay, now where did this restriction that n is greater than 30 come from? Anybody wants to guess, or anybody knows or remembers? Please? Central limit theorem, that's right. The book gets into more detail. I don't want to get into more detail, just to say that the way this formula was derived was by approximating the binomial distribution via a normal distribution. When you take a binomial distribution, which looks something like this, you take this shape, as n grows, this shape looks more and more like a normal distribution. And that formula that you saw is actually a formula for approximating, for statistical inference for the mean of a normal distribution rather than the mean of a binomial distribution. But for n greater than 30, it's a pretty good approximation. So the book has a lot more details to refresh your mind about what a normal distribution is, its mean, its variance, how well it approximates the binomial, and what the derivation is of the confidence interval for normal distribution. This is it's very important. Everybody should know that, but it's not machine learning. It's a little well-known, well-defined, fully mature branch of statistics that you should have had either in undergraduate education or picked up somewhere along the way. If you don't have it, if you don't remember it, or even if you do, go back to the book and read that chapter. If it's all very easy and familiar, then it won't take you very long to read the chapter. It'll just be, yeah, I know this. And if not, then you'll be grateful for having done this. It's really important. I want to keep you here at the higher level, at the level of why we're going through all of this. We're going through all of this to solve question number 1. Given a hypothesis, what is its true error? Well, we don't know what its true error really is, but we're going to use the confidence interval methodology for putting bounds around it. The bounds are going to depend on how big the sample is. The larger the sample, the smaller the bound would be. You see it with the dependence on square root of n in the denominator. It's also going to depend on the inherent standard deviation, which is that p times 1 minus p, or error sub s times 1 over 1 minus error sub s. So errors that are near 50% are going to have the highest standard deviation, and therefore will give us the biggest intervals. But typically our errors are going to be much less than 50%, right? If you're going to come up with a hypothesis, probably its error is small, 5%, 10%. So that would actually work to our benefit. And the third thing that influences the size of your confidence interval is how much of a chance you're willing to take that it will not be a correct confidence interval, namely it does not capture the true value. So these three things interact. Sample size, tolerance of failure, and standard deviation. It turns out that the same procedure we use is going to be used to solve all three problems. So I'll repeat the steps that are typically taken, but I think I have a good slide for that. Okay, the general way of doing things to solve these three problems and other related problems that are not discussed here but you may come across is 3 steps. Step 1 is pick the parameter to be estimated. Step 2 is choose an estimator. I'll explain all of these one at a time. I'm sorry, 4 steps. Step 3 is determine the probability distribution of the estimator given the parameter. So step 4 is calculate the confidence interval, or derive the confidence interval formula. I'm going to first describe it abstractly. Pick parameter to estimate. Statisticians like to use theta for a generic parameter. So I use green for parameters that are not known to us but supposedly are fixed. I'm going to use purple for data or functions of the data that are known to us when we do statistical inference, or statistical estimation. And the estimator, statisticians like to use a hat over a parameter to denote an estimator of that parameter. So in this case it would be theta hat in purple. And I'm going to remind you that it's function of the data. Anything that it's a deterministic function of the data is going to be in purple. Step 3 is to determine the probability distribution of the estimator. The estimator is theta. Because it depends on the data, it has a distribution. It's the distribution of the estimator given the true value of the parameter. Green is the true value. It's fixed. It doesn't change. We may or may not know it. Purple is the data. If you have one finite sample of data, it's fixed. But when you think in terms of probability theory, it's a distribution over all possible outcomes of data. So let me put these colors here. The parameters are green. This P here is green. This mu and sigma here are green. Data outcomes are purple. For example, these x1, x2, xn are purple. 7 heads out of 10 is purple. Probability theory starts from green and goes to purple. Statistical estimation starts from purple and goes to green. When you do probability theory, you assume a fixed green, and you say that the purple can vary. It's a distribution. You could have many different possible data. When you do statistical inference, the purple is fixed, because you got one set of data. You know you could have had a different set on a different day. But right now, today, you have one data set. And you try to use that data set to infer the range of values that green must have been in. To infer in what range green must lie. Okay, so now that we have the colors, let's go to our sequence. First, you need to identify what parameters you're estimating. That's green thing. Then you need to choose an estimator, which is a function of the data. Then you have to write down explicitly the relationship between the value the estimator will take the probabilistic relationship between the value the estimator is likely to take or can take and the true value of the data. And then you invert this relationship and derive the last part. So 3 is going from green, is figuring out how theta, the green thing, probabilistically gives rise to theta hat. And 4 is determining how, from theta hat, we can infer something about theta, which is just green. So now we're going to rehash it for the first case and then see how we apply it to the other two. So in the first case, here's my white here. The first problem, what is theta? What is green theta? Somebody. What is the true parameter that we're trying to estimate? True error. Error curly d of h. What is theta hat? Which is a function of the data. Somebody else? Somebody else? Somebody else? What is theta hat? The hallmark of something purple is that you can look at the data and calculate it. You're not estimating it, you're not guessing, you're just calculating. It's a simple function of the data. Please.
Error S.
Error S, that's right. Error S of H. Even though these two look very, very similar, they're very different, which is why they have two different colors. One is a fixed number that is unknown to us, a fixed parameter that's not unknown to us. The other one is very well known to us once we have the data, but it can assume different values in different data. A simple function of the data that is used to estimate something else is called a statistic. A statistic of the data. This is where the term statistics come from. A statistic of the data is some simple function, typically simple function of the data that you're given the data, you can calculate it. Okay, I'm sorry, I didn't write here. This is number one. This is question number one. The third step was determine the relationship between the true parameter, the green thing, and the data outcome, which is probability of theta hat given theta. And I'll put the colors in a second. What was it in our case? I should add here something that might be, just to reduce confusion, hopefully it would. We're also assuming some sample size. So you could have this n as part of your data, but we can assume that n is fixed. So we decided in advance we're going to have exactly 100 items in our test set. Nonetheless, what is this in our case? Tom? The binomial. This is the binomial. This is the probability that the number of errors. So this would be the number of errors, probability of error sub s of h, if you define it as k out of n. So it could be either k over n like this, or if we define it as just a number of errors. Given the true parameter, is the binomial. I'm not going to reproduce it here. And then our fourth step was to calculate the confidence interval, which means green say, call it green 0. Well, no, it's not green, I'm sorry, it's purple. It's derived from the data. Call it purple theta 0, which has our best estimator, our 0.7 in the example we had, plus or minus something like this. Something here. This is the formula I showed you. This is the confidence interval. And what we say is that the probability that the true value is in here this is a confidence interval. This is in purple too. This determines some from and to, some interval. The probability that the true value is in this interval is quite large. It's greater than some 1 minus delta. It's greater than 95%, greater than 99%. I just rehashed to you what we've already done before, but put it in the language of this formulation. Questions so far? Now let's do the same thing for the other two questions. So question number 2 is, given two hypotheses H1 and H2, and maybe I should call them HA and HB to make it more... Now, let's keep it H1 and H2. Which hypothesis is better? Or specifically, is H1 better than H2? And by better we meant having a lower true error. Right? We realize that the error on some finite set is not the whole answer. Because on one finite sample, H1 might look better, on another one, H2 might look better. What we're interested in, and what is very well mathematically defined, is the true error. We may not know it exactly, but we can define it. What would be our statistic of interest? Pick a parameter to estimate. Can you think of one parameter to estimate that when it's greater than 0, you can conclude that H1 is the same as saying that H1 is better than H2. And when it's smaller than 0, you can say it's not better or worse. Sorry? I hear something? H1 minus H2. You mean the true error of H1 minus the true error of H2. Yes, so that's what we're going to do. Number 2. Our true parameter is going to be true error of H1 minus true error of H2. Now this is all in green. Why is it in green? Because it is something fixed that God knows. We don't know it, but it is knowable. It is something fixed. Once you give me H1 and H2 and curly D, it is well defined mathematically. And it has a fixed number. It doesn't vary. It's not purple. It has a fixed value. It may be greater than 0, it may be lower than 0, it may be 0, we don't know what it is, but it's there. Ultimately, we're trying to capture it, right? Okay, number 2 is choose an estimator. What's going to be our estimator? I need purple for that. What is our estimator going to be? Okay. Error under S of H1 minus error under S of H2. This is purple, because this changes based on what S happens to be. S is randomly sampled. So one day it would have one value, on another day, with the exact same world, with the exact same green value here, it will have a different value. It's very similar to the situation here, because the situation here, first of all, you can see, the relationship between this and this is very similar to the relationship between this and this, but it's deeper than that, because we're relying on the variability of the same sample. Here we're acknowledging that on different days we'll get a different sample, and therefore the estimator would have variable answers. And here we're relying on the same variability of the same sample. It's just that instead of estimating the error of a single hypothesis, we're estimating the difference between two hypotheses. But other than that, it's kind of the same thing. And as a result, the formula we get for number 3 and number 4 are also very similar. And let me show you what the formula is for the confidence interval for the case of two hypotheses. This is the entire 4 steps on the slide. The first one is pick the parameter. They call it D here, we called it theta. That's the difference between the two errors. I brought my nifty pointer. Here it is. The difference between the two errors, this should be green. Step 2 is choose an estimator. This should be purple. The same hat over particular set S1. Here, interestingly, they use 2 different sets. Let's forget that for a moment. Step 3 is to determine the probability distribution that govern the estimator. Right? Step 3 is playing the game of probability theory from green to purple. So presuming or pretending that we know the true value of the parameter and looking to see how the estimator behaves as a distribution. And that's done here, and it looks very similar to the first case, except instead of having a single expression like this form for the standard error, we have a sum of 2 expressions. One that came from the first sample, one that came from the second sample. So 2 variances that kind of add together. And then step 4 is to take this, invert it, and come up with a formula for the confidence interval that says that with very high probability, with n% probability, the true parameter falls in the range of the point estimator plus or minus the confidence length. Very, very similar. The differences are slight. And if you go back in the book, you go back over the slides, you can put them next to each other and you'll see where the differences are. Let's talk for a moment about the fact that there are 2 different samples here. Let me ask you sort of an intuition question. Suppose you had 2 hypotheses, H1 and H2, and you wanted to answer this question. And you had 2 choices. You could either evaluate them both on the same sample, or you could evaluate them on 2 different samples. Sample sizes are always the same, 100 data points. So either you're evaluating both on the same 100 data points, or you use 100 data points for this one and a different 100 data points for this one. Which would you prefer? Same. Why? Please?
If a single hypothesis varies between 2 different samples, then pretty much assume the other thing the same for both hypotheses, that the true error will be different for each sample set. So without using the same sample, there's no way of accurately comparing them.
Okay. I wouldn't go that far as saying there's no way of accurately comparing them. I think they're both legitimate way of comparing them, but I see why you have a preference for one over the other. And I agree with that. I just wouldn't go as far as you said. If you had a large enough, let's say it wasn't 100, it was 1,000,000, and you'd feel a little more confident, even though if they were not the same million, right? So it's a quantitative difference rather than a qualitative difference. It's not that you cannot answer the question which one is better with different samples. It's just that you need more data to reach the same level of confidence, perhaps? Please?
I was going to say, because you can make some assumption that what might be bad training data for one is likely to be bad training data for the other. Guaranteed, but you would expect...
Testing data, you mean? Bad testing data, you mean? There's no training going on here. Yeah, okay. Okay, yeah, you're talking about the same thing. So intuitively, you test a class, you give them an exam, you don't want to give them two different exams, right? That would not be fair, because one of the exams might happen to be a little harder than the other. Right? So this is the same situation that you guys are talking about, that there is intrinsic variability of the test sample itself. It could be harder or easier, and even though the way you chose it for the two samples was unbiased, namely you did not deliberately make one of them harder, even without deliberately making it harder, even you use a fair procedure, due to fluctuations you may end up with one sample that is harder than the other, and then you're not estimating them the same way.
Is it implied in the formula?
I'm sorry?
Is it implied in the formula?
Yes, I'm going to get there. It is implied in the formula. So one thing I want to emphasize in my answers to the first answer is that it's not that you cannot do it that way. You can do it that way, but it is less efficient. You will need more data, larger sample size, to reach the same level of the same reduced confidence interval or the same level of reliability, and you can see it in the formula. If you derive this formula, you don't see here the formula based on the same S. But if we had developed it under the assumption that they are subject to the same sample, we would end up with a confidence interval with a standard deviation that is smaller, and therefore with a confidence interval that is smaller. And smaller confidence interval is better. Sometimes in the real world you're in a situation where you don't have a choice, where you have to use maybe the behavior of the hypothesis is not known on a common data set. It's known on two different data sets. Maybe you've unearthed some old hypothesis from the literature and it was reported on some set, and you don't have access to that set anymore, so you cannot compare your new hypothesis on it. That actually happens a lot, not particularly this setting, but in the real world when you compare two explanations, sometimes you cannot compare them on the same data. That's okay. It's not a party breaker. You can still continue, but it's not as good as if you can evaluate them on the same data set. If you evaluate on the same data set, you have more efficiency of data. That's called a match testing, or match comparison, or matched data statistics. All goes by the name matched. If you match it on the same set, you need less data to draw the same strength of a conclusion. You can understand it intuitively, of course, but you can also see it mathematically in the confidence interval derivation. We don't have here the second derivation, but I think it's in the book. And if it's not in the book, it's not difficult. It's simpler than this one. It's simpler to draw. Okay, let's do number 3. What is our parameter of interest? To remind you, number 3 is, given two learning algorithms, which one is better with regard to producing a lower error or more accurate hypothesis? Go ahead. Please.
The error on training sets.
The error on what?
On a large number of training sets.
The error on a large number of training sets. Okay, so the underlying parameter is the average error of hypothesis produced by learning algorithm 1, or A, when averaged over many, many training sets. Okay, so let's first write here the average error, the true error. Suppose it's the true error, so it's green, error curly D of H. But which H is it? We don't have a fixed H. This has to be averaged over all H's that are produced by the learning algorithm A over many training sets. Then?
Is it many training sets or all training sets?
Well, it's the expectation over all of them, right? You're right. Many is a finite number, and that would be purple. It's the expectation over all of them. So the way we're going to do it is we're going to write this is the result of applying learning algorithm A to, this is the error of H, which is the result of applying learning algorithm A to some set S, and this is taken as expectation over all sets S that are drawn from curly D. I don't know if I should write everything in green. I think it would be more accurate for us. Let me write it in white so that it's not controversial, but I'll write the important part in green. The reason it could be controversial is because the true error is always green, right? Except that now we have a distribution over possible training sets, which is here. So this part is purple actually. This is purple because drawing a sample of training examples is a random variable. It's a distribution, a purple distribution. Then we take the sample, we apply the learning algorithm to it. The result of that is a fixed hypothesis. A fixed hypothesis has some fixed error with regard to curly D. We don't know what it is. Now we repeat that in principle infinitely many times. We take the expectation of it over all samples of, say, a fixed size drawn from curly D. When you take the expectation of something, it becomes green. Okay, so that's something to keep in mind. When you have something purple and you take its expectation, it becomes green. Why? Because the purple means it has a distribution of values. It's a random variable. When you take the expectation of a random variable, you get a parameter. So the overall thing here is green. And now we actually do it twice. We do this minus the same thing minus the same thing with regard to the second expectation, ST, error curly B of LB of S. Sorry. And this is our parameter of interest. Sorry. This expectation minus this expectation. Question?
Is there a reason to use a different symbol for S and T to expectation?
For S and?
No, like you have S squiggle D for
this?
Yeah.
This is my clumsy attempt at erasing. I didn't decide what to do here. I think both of them should be tilde. Like S drawn from, well, is this drawn from? I don't want to say every possible subset of D. That would not be right. I want to say S drawn, sampled from D. I think squiggle would be, should be the same here. Let's say we fix N, and in fact, it's important to fix N because the overall answer could be different for different values of N. You could imagine two learning algorithms. One of them is on average better for small data sets, and the other one is for on average better for large data sets. So if you determine in advance that the size of S that you're going to sample as your training set is 100, the true parameter value, the true green thing here, might be positive. And if you determine that n should be 1,000 or 1,000,000, it could be negative. So we have to fix n. Once we fix n, so I should edit here, s equals some fixed number un. The value of s is some fixed number n. Same n. Once you determined a fixed size of your training set, now the problem is well defined, and you're asking about the expected value of the true error. Operationally, you're going to do it by sampling many times, but this doesn't come into play here. Here, this is still defined in green land, not in purple land. In green land, you're not repeating something many times, as Dan pointed out. You're effectively doing it infinitely many times. You're asking about the expectation over all possible samples. Okay, that was step 1. Step 2 is defining your estimator. How would you like to define the estimator for this particular green theta? What would be purple theta hat? Remember, it's purple, so it has to be some well-defined, calculatable function of the data.
The error over the test set of the result of the first algorithm over a training set minus the error over the same test set of the result of the second algorithm over the same thing.
Okay, so it's effectively taking whatever data you have, dividing it into training and test, training both algorithms on the training part, testing them both on the test part, and subtracting one from the other. That would be one statistic. It won't necessarily be the best one. Can you think of what would be a better statistic? One that would result in lower standard error, right? It would result in more accurate confidence intervals. Still, with the same amount of finite data that you have, what can you do? It's as if I'm saying to you, take a coin and flip it once and use the outcome to estimate the probability of head. It's okay in the sense that it's unbiased, but it has very high variance. How can we reduce the variance? We can do it by repeating the training-testing split many times and averaging over the result. Okay? So both, is that what you want to say then? Or something else?
Can we do n and take a lot of training sets of size n and do an average over n?
If you could have access to as many training examples as you want, yes. But I was asking a slightly separate question. You have a fixed amount of training data. What statistics would you define then? I mean, ideally, if you can derive as much training data as you want, then you operationalize this by doing what you're saying. Fix an n, draw n examples, train on them, draw some other number of examples, test on them, throw it out. Take another set of n examples, train on them, get potentially different hypotheses, test again, repeat that many times. In practice, we have a finite amount of data, so we're going to take the same finite pie of data and divide it one way for training and testing. Train, derive the hypothesis, calculate the error on the test set, subtract, keep it aside, then break this and put a division somewhere else, and repeat that many times. Okay? That would be a statistic, well-defined statistic. Then you can calculate, number 3, the probability distribution of that statistic, and then you can invert that to get the confidence interval. We will rehash this part at the beginning of the next lecture. Okay? Thank you.